Okay, welcome. Second part of logistic regression. After today, in principle, you know all there is to know about logistic regression, and the rest is a bit of practice. So let's see where we can end today. This was the general setup that I've shown you before. In gray, all the stuff that you have learned, or at least have seen in the second methods course. In blue, what we still have to do. So factor analysis is actually the third topic. Will be away at the end. Mixed models or multi-level models, that will be the next topic that will start this Friday. And logistic regression, there in the red, that is what we're doing now. So we are in the part where, in principle, you have dealt with your data already, in the sense that all the data is collected, it's cleaned, you have all the variables ready to go, and now you're predicting something that is binary, for which we need logistic regression. Just a reminder, okay, nothing to be scared about, unless you were scared about multiple regression, because it's largely the same thing. There's a different way to estimate coefficients. It's called log likelihood maximization. And you need it because the standard way of trying to fit a line through a cloud of dots doesn't work very well anymore. That method is really, well, it has its bad sides as well. It takes longer, it may not converge, so all that is not so nice. But it is working in principle for basically any kind of model you can come up with. So as long as you have a model that has a reasonable representation, then you can use this same method. Then interpreting the output, well, there we saw already largely the same thing. Again, a regression type output. Somewhere over here, a measurement of how well the model is fitting. Somewhere over there, the coefficients and whether or not they are significant, and confidence intervals that go with it. And the only thing that was different was the top left, where in regression we had sums of squares and these kind of things. And here we have simply an overview of the iteration log of the log likelihood method. Okay, all we did was look at that last week. Interpretation of the coefficient was, well, as long as you're only interested in a direction, it was relatively easy. Positive coefficient, that goes with, okay, the larger x is, the larger the probability that y is a 1. And the other way around as well, so that's just fine. But we already saw that interpreting the exact size was not so easy. You get that all these things sort of mix up together, unless you do something that is, well, easier in some sense, but also more complicated in another. If you're getting used to interpreting the whole thing in terms of odds ratios, the probability of y equal to 1 over the probability of y equal to 0, then you get rid of most of the issues that we had. And we'll see here that there is another command that can help us try to interpret what the size of the effects actually is. Okay, so this is the standard regression or logistic regression run, also seen quite a few times before. What we're still missing is the checking of assumptions that we normally also need. The good news is here this is way easier, or at least less work. Checking and dealing with outliers is largely the same, as we will see, but requires actually a different command. So these are the last bits that you need to, in the end, be able to run any kind of logistic regression analysis, including the one the first assignment that we had online. I think last time the stuff that I covered was good enough to bring you all the way up to question 4 or 5 or so, and there were, I don't know, 11 or 12 questions. After today, you should be able to do these, I think all of them. These are the commands that we'll see that we have not seen before. One is called margins, lsens, where the sense is for sensitivity, and I guess the L is for logistic. lroc and link test, well, we'll see all that during the rest of the day. Okay, one brief intermezzo. I now have, I think, almost all of the data from ourselves complete. So the whole survey that you took somewhere in the beginning of week 1, most of you that I now have put online. So that includes the PDF with the actual survey, because I assume that it's convenient to have the actual questions with it and the data set that we have. So we now have 80 cases. And there are a couple of variables that I want to mention here, because the example that I'll show is based on these different variables. So one is a variable that's called high grader. I have actually an answer to the question, what is your average grade, and then up to the level of half points. But I needed, for the example, for logistic regression, I needed something that is binary, so I created, okay, if you have a 7 or higher, you are a high grader, and otherwise you're not. That's the one that we're going to predict in the examples. Then there was a longer set of items that was, at least in part, supposed to measure conscientiousness, the extent to which you pay attention to detail, loosely speaking. People argue or have argued that this might be a decent predictor of your actual grade, so we'll see if that actually works. There was another item battery in there that was all about the ways in which you decide. I created a scale score from that, and I labeled decide irrational. Doesn't really matter exactly what was in there at this point, but at least that's another variable that we take from our own data. And the variable male is simply, well, equal to 1 if you are, and equal to 0 if not. And I cannot emphasize enough, it is good practice in dealing with data to come up with variable names for binary variables that have a name that fits the actual coding. So if I have a variable that's called male, it will always be equal to 1 if male, equal to 0 otherwise. Quite a few times you'll see in SPSS, for instance, that people code this as 1, 2, or even as gender and then 1, 2, and then you have to check back all the time, okay, which one is the 1 and which one is the 2, and you get rid of that simply by renaming the variables in the right way. If you browse through the data, then you'll see that there is a variable in there that's called P code for personal code. That's the code that you typed when you wanted to be able to find yourself back in the data. So that is the line, the row of data in the data set that represents your actual answers. Might be of interest as soon as we get to the factor analysis part, for instance. These are measurements of all kinds of things about you, and you can see how you compare to the rest of the group. Okay, so high grader, conscientiousness, decide irrational are variables that we're going to use to predict. Conscientiousness is interval scaled, decide irrational is interval scaled, male is obviously binary, and high grader is also binary. Okay, so this is what we had before as well. There are two ways to interpret the size of the coefficients. One is relatively easy intuitively to understand, but not so easy to do. That is, okay, I simply look for a predictor variable. Let's say male. Male can be 0 or 1. If male is equal to 0, what is then the predicted probability? Let's say 0.3. If male is equal to 1, what is then the predicted probability? 0.8. Okay, so I know that now the effect of male is, well, it can bring you from 0.3 to 0.8. Fine. The only trouble with that is that that difference, 0.3 to 0.8, depends on the values of other predictor variables in your model. So if you have conscientiousness in there, or decide irrational in there, or anything else in there, then depending on the value of that variable, you get differences from 0.3 to 0.8. Or if there's another positive variable in there that has a positive coefficient and very large values, it might be that on that flat S that you have in logistic regression, you're all the way over there. So now the differences in probability are necessarily very small, and you'll find, male equal to 0.99, male equal to 1.991, and then it appears as if the effect is really small. Okay, then the only thing that I said about these probabilities, if I remember correctly, is just that this issue is there, but not how you can get a feel for what's going on there. And there is an actual command for that. It's called the margins command. Here you see the baseline logit that I ran. Logit, high grader, conscientiousness, decide irrational, and male. And note the I dot in front of the male. I'll get back to that in a minute. And let's see what works here. Well, we see that indeed, oh no, actually this is against standard theory. If you're scoring high on conscientiousness, there is a negative coefficient there, then the probability that you are a high grader is actually lower. This is not our own data, but this is the data from, I think, 2 years ago or so. So the first thing that I would do if I see this and do this, let's say, seriously, is double check how I coded my conscientiousness variable. Because if accidentally I reverse coded this, then it might be totally the other way around. But still, there is a significant effect. Decide irrational, if you score high on that, then the probability of being a high grader is larger. Again, a bit weird, I would say. And, well, actually not significant with a level of 0.095. Being male, yeah, you could argue doesn't make a difference because not significant. But given the positive coefficient, you do see that males apparently in this data set had a slightly higher probability to have high average grades, or have a slightly higher probability to say that they have a slightly higher grade. That could also be the case because we simply asked, okay, what is your own grade? Okay, but we need the margins command for this. Now I want to know what the effect of male actually is in terms of probabilities. Let's see how that goes. Oh yeah, first, this is all the stuff behind the scenes. So the predicted probability, you see here on the top left, that a person is a high grader, well, defined as 1 over 1 plus e raised to the power of minus, and then that thing between the brackets, that's your standard thing that you see in multiple regression as well. And the only reason that we have that 1 over 1 plus e raised to the power in there is to make sure that this all turns out to be a probability, a value between 0 and 1. So give me the value of conscientiousness, of decide irrational, and of male, and I'll give you a probability. That's the idea. Okay, now I need to be able to calculate these, and there are two ways to do it, each of which are actually fine, and the trouble is that both might lead to different answers. So one solution would be, let's first start with solution 2 actually, because it's the easiest one. If I want to know what happens for male equal to 0 and male equal to 1, I also have to say something about these other variables here. So what I could simply say is, okay, forget about the other ones. I'll stick with conscientiousness at the mean level of conscientiousness, whatever that mean may be. And for decide irrational, I also take the mean of decide irrational. Then I have that first part there. These ones I have estimated, B0, B1, B2. Here I plug in the mean of conscientiousness. Here I plug in the mean of decide irrational. And then I only have to calculate the probability twice, once with male equal to 0, once with male equal to 1. And I get my difference in terms of probabilities. That's actually solution 2, and it'll work. It's not the default in Stata, but this will do the trick. The other way to do it is slightly different. What you could also do is, well, think about what your data looks like. We have 3 columns here that are predictor variables, and 1 column that is the thing that you're trying to predict. These 3 columns, some of them will have male equal to 1, some of them will have male equal to 0. What I could do is calculate all predicted probabilities, and then once with all values of male set to 0. So in the cases where male is 0, do nothing. In the cases where male is 1, plug a 0 in there. Calculate all the predicted probabilities as if all the people in your data were females, and average that number out. Okay, remember that. And then do it again. Now with all male set to 1, so as if all your data is containing males. Again, calculate all the probabilities, average that number out, and then compare these two. So again, you end up with 2 probabilities saying something about the size of the effect, but slightly calculated slightly differently. Okay. Anybody for whom I need to do that again? Perhaps for you, you look very puzzled. No? Everybody okay with this? 2 ways to do it, and with all the things where you can do it in 2 ways, you get into trouble if both ways lead to different results, because then you have to think about which of the 2 is the most reasonable given what you're interested in. But let's see how it works. Here I put the original command back because in a minute I will type the command margins male, and that will work. But it will only work because here I have put i.male in the original logit command. The I dot tells Stata this is a categorical variable, in this case with 2 categories, and then Stata will remember it. If you would have typed simply male here, then the logit regression would have run, just like the one you see here, no trouble whatsoever, but the margins command would not have run. So if you have categorical variables here, then it's easy to add the I dot in front of it. If you have that, fine. Now you can type margins male. You see this twice on the top left. This was actually, for a minute I thought that I interchanged what solution 1 and 2 is, but I didn't. If I type margins male, then I get the complicated ones with all zeros and then all ones, calculate all the predicted probabilities, average them out, and then calculate the difference. That's by definition what Stata assumes that you want, and in this case you see that for male equal to 0, the predicted probability is 0.38, and for male equal to 1, the predicted probability is 0.57, which gives you a sense of how large the effect actually is. If you would have had another binary variable in your predictor set, I don't know, age over 40 or whatever, not in our data, not very likely to have any cases, but let's say age over 21 or so. That's also binary, and if you do the same analysis and would get, okay, there the effect is running from 0.22 to 0.23, apparently this effect is really small, and this one is, well, in the order of magnitude of 0.2. What you see here is that if you type the at means option, so sticking the other variables at their mean, and in the output you even see what the mean is. For conscientiousness, you see that it is, well, effectively 0, and for decide irrational that it is 2.4. Then this is imputed, and you'll see 0.36 versus 0.59, so say loosely the same kind of size effect. Okay, so this will help in trying to interpret what the size of the effect actually is. Is this something we should be bothered with, or is it actually a really small size effect? And that's not easy to see just from the coefficients in the logistic regression. Okay, now, besides male, we had two other variables, both of which were would be nice if you could now type margins and then the interval scaled variable. In this case, I took conscientiousness. And then Stata will complain. Factor variables may not contain non-integer variables. What Stata tries to interpret here is, well, you're saying margins and then just a variable. And then by definition, it assumes that it must be categorical. And it sees from the values of that variable that it's not. So it complains and says, okay, something's wrong here. I think that you're supposed to mean a categorical variable here, but that's not what's happening. So what you do here is instead, you look at the variable conscientiousness in your data set and you check what the range of that variable is. Apparently, in this case, it's ranging from minus 1.5 to plus 2.5. And then, and this is, I must admit, a command of which I easily forget the syntax myself with all these brackets and where you need to put them. But if you type this, margins, then a comma, at conscientiousness equal to, and then a larger set of values, and here I took minus 1.5, minus 1, minus 0.5, and so on, but you know, you could have taken more or less, you can choose whatever you like. Then you get back, for all these different values, the predicted probability, as you can see there. So this is saying, okay, that first value that you had, the minus 1.5, that will give you a predicted probability of 0.75, and the last one, that one over there, will give you a predicted probability of 0.11. So if I vary conscientiousness across the whole range from minus 1.5 to plus 2.5, my predicted probability changes from 0.75 to 0.11. So in terms of size of the effect, this is actually bigger than the size of the effect of male, because that was only 0.2 over the whole range. Again, by default, Stata will use solution 1, and if you want this to run at the means of the other variables, fine, you can do that too. And then you simply type at means behind it. Yeah, there and then there. Okay, then still, it's not so easy to see exactly what's happening here. I mean, you can look at the endpoints, 0.75 and 0.11, and then you know the overall size. But all this is based on that flat S that is somewhere in between the data, so to speak. So if you for an actual plot right after you type the command is margins plot, then you'll get back exactly what you have estimated here. And then this, take a close look at what I did there. So this first part up to there is the same as on the previous page. Margins at, well, conscientiousness equal to, and then the list that you want to see. And I immediately added another variable that I also wanted to see, male equal to 0 and 1. So now you get back, if you ask for a margins plot, a plot that looks like this. And this will allow you to see, well, for instance, for males equal to 0, that's the blue line. You see a difference from, on the left, 0.66 or so. to on the right, well, let's say 0.1, and loosely speaking, the same size effect for male is equal to 1. The red line, the difference between the left and the right, is about the same. You also see that the difference between male equal to 0 and male equal to 1 is, yeah, slightly higher perhaps over there and slightly smaller over here, which is not so strange. Usually at some of these ends, the probabilities get closer together. Here, when you are already very low, 0.1, then there is not much wiggle room to play with anymore. So you can see what the lines look like. In fact, here they do look quite similar for both cases, but what could happen here is that these lines, for instance, even cross. Could very well be. Okay. Let's see. Oh yeah, and I didn't put that in here, but if you actually type this command, you do get output. You now get output with predicted probabilities for all the different combinations of values that you have tried. So minus 1.5 with male equal to 0, minus 1.5 with male equal to 1, minus 1 with male equal to 0, and so on. I got rid of that output because yeah, then usually it's not so intuitive anymore what's happening. You ask for the plot and then you can see what's happened. No problem. Okay, any questions up to here? Because that is basically what we have in terms of interpreting the size of the coefficients. So one typical question would be, run a logistic regression analysis, look at what you find, and try to figure out which of the variables here seems to have the highest impact on the target variable. And for that you have the odds ratios from last week, and you have that margins command to plow around a little bit and try to see what the effect on the predicted probability is. And that's it. What we have. We have nothing else. Everybody good to go with that? Okay. Then, regression assumptions. Yeah, the good news is, because of that whole likelihood stuff that we did last week, the things that we need are a bit easier than before. There's not such an elaborate list of things that we need to check. It's still a bit of a list, but it is way less. Let's see. First of all, if you type what are the assumptions of logistic regression analysis and then Google that somewhere, you'll find that you'll get different kinds of answers. It's not exactly the same everywhere. So in the light gray on top you see the things that, well, are more or less assumed automatically without really checking, so to speak. So no important variables omitted. It shouldn't be the case that you're trying to predict a target variable, that there is a really important predictor that you simply do not have. Yeah, okay. No extraneous variables are included. So if you have lots and lots of variables, none of which actually correlate to your target variable, yeah, if you have a couple, fine. If you have 40, then this starts to be problematic. It's like looking at your data through a haze of noise, and you want to get rid of it. Then what we also assume all the time, also in multiple regression, but never bother with much, is, well, actually what you're assuming is that all the predictor variables are measured without error. And that's actually a big thing. In general, what you get is if the variables are measured with error, as they usually are, the coefficients get closer to 0. So it's more complicated to find an effect even if it's there. So if you can easily imagine this. Let's suppose that you have huge amount of error. Let's say almost all error. Yeah, this is the same as that you have noise. And if you have all noise, then you have all coefficients equal to 0. So normally, a lot of error in your measurement will make that you do not find effects, even if they are there. And what we do need very hard here, it's not easily tested, but you have to think about it before. And that we really need in the likelihood story is independence of the cases. That likelihood story started at some point with, well, we can look at what the model suggests the data is coming from, and then look at the coefficients in such a way that, well, we hope to find the coefficients that actually maximize the likelihood of the data. And for that, we assumed that we can separate these probabilities. The probability of getting the whole data is the probability of getting the first case times the probability of getting the second case, and so on. For that, you need independence. If you don't have it, then you're screwed. Influential data points, yeah, not really sure if that's an actual assumption. I think in the regression list we didn't even include that this is an assumption that you shouldn't have too many of these. We'll have a look at what the influential data points are and how you can find them in a minute, but yeah, you could argue about if this actually is a assumption. No multi-collinearity, that we had before. That was when your predictor variables correlate very highly. You don't want that, so we have to test for it. Then something that says something about the fit of the whole model. That we had before in regression as well. There the command was called OV test. You want to have that the prediction model that you try is sort of a decent fit for the data and an equally decent fit everywhere. We can test that with actually number 3 and number 4. And that Hosmer and Lemeshow is another way to figure out if the fit of the model is good enough. Okay, so let's see. First, influential data points. I think last time or the time before that, I asked if somebody remembered how that worked. And I also remembered that basically nobody knew. The point that I tried to make there is, well, we had a command that was called Idfbeta, and that we used in regression analysis to figure out what the outliers are. Okay, if you don't remember what that was, check back again. And it would have been nice if Stata would have allowed us to type Idfbeta also after logit, but it doesn't. We need a separate command for that, and that separate command is called Idfbeta, with the L for logit, and you have to download it. If you type net search Idfbeta, you'll find it, and you can run it right after a logistic regression. I think I have an example actually here, so that you can see it happening. So you install this command once, then it will work, and here you see this happening. The top left in the small here, this is again using the standard auto data set from Stata, logit, foreign, price, and miles per gallon. So the thing on the top left is simply a logistic regression table, nothing new. And now you get a couple things. First, typing Idfbeta, as you see here. That gives you as many extra variables in your data set as you had predictors in your model. Here we had 2 predictors, price and miles per gallon. We get 2 variables back. Idfbeta price and Idfbeta miles per gallon. These, should I go through what that is? Probably doesn't hurt. Okay, so what you get back, let's look at this one. Idfbeta price. For each and every case, you check if I rerun my logistic regression analysis, and now with this first case excluded, then I again get a regression table, and I can look at the coefficient of price and see how much it moved. Okay, what you don't want to have is that you take out one case somewhere, and then your coefficient moves enormously. Okay, it's 0.0002, and now I take out case number 34, and now it is 8.5. Okay, that's weird. Apparently what I get is dependent to a large extent on that single case. This is why it's called an influential case or an outlier. And we have to try to find these cases and think what we should do with them. And the way to do that would be, well, first you create these variables. In these variables you see how much the coefficient will move if you take out that case. And then the easiest thing to do would be you standardize these variables. Standardizing, subtracting the mean, dividing by the standard deviation. If that thing was normal, like this, it will remain normal, but with a mean of 0 and a standard deviation of 1. And the good thing about that is, now we know what extreme values are, because extreme values start, let's say, above 0.3 and below -3. So if I do this, create these variables, now I standardize them, and now I look at these variables to see if I have any extreme cases there, and here I see values ranging, well, this is way below -3. So this is a reason to look at the cases that have values below -3 here. This is also below -3, so also for miles per gallon we have a couple of cases that lead to some trouble. And on the positive side we do not see any really extreme values. So what I would do next here, go to my data, I'm going to find the cases that have a value smaller than -3 for these. I'm going to look at these cases, perhaps there's something weird about it. If I understand where the weirdness is coming from, for instance, all cars in the data are non-diesel cars, and the ones that are outliers are 2 or 3 diesel cars. Okay, now I understand why they might be different. I create a new variable equal to 1 if the car is diesel, equal to 0 if not. I rerun my analysis, and now I hope my outlier is away. Okay, for all these kind of things, there is a bit of hand waving involved, because I now say -3 to +3. Yeah, this is a very crude rule of thumb, largely based also on the size of data sets that I'm used to. If you have a data set, this is 74 cases, which is kind of low, but if you have a data set with 100,000 cases, yeah, then even for a normal distribution, there will be quite a few cases below -3 and above +3. Okay, so then by definition, you're going to find outliers. So you have to keep in mind a little bit that, yeah, let's say how normal it is to find these cases above 0.3 and below -3, and adapt as you see fit. One way to find them also is simply plot the variable in a histogram. If it's normally distributed and it looks like this, okay, that's basically what you would like to have, and could be consistent very well with no outliers. If you see something like this, and a little hump there, okay, these cases are the ones to look out for. Something's strange there, and you have to check your data and figure out what's going on. Okay, questions up to here? Sounds easy, perhaps, or reasonably easy as separate entities. You know, well, the Idfbeta, I can do that, but if you have to do it all together, then it starts becoming more complicated. Okay, yeah. Finding outliers, in principle, yeah, the only thing that you want is let's say, a reason to look. So even if you have a rule that's not really appropriate to use, as long as it works in the sense that it pinpoints to you, now I understand, these cases here are weird, then it has worked. So one quick and dirty way to do it, instead of what I just mentioned, logit yx and then the Idfbeta and so on, is simply run the same thing, but then through regression. Okay, this is not what you're supposed to do here, but nevertheless, let's do it. Regress yx, and now type that diag2 command. We've seen that before. What that does, that also looks for outliers, but then after regression. So we could just pretend as if we do not know that standard regression is not allowed here, and try to look for outliers here too. Might help you find a couple of weird cases that shouldn't have been in there. Might lead to that you find some coding errors somewhere. Anything that can help you pinpoint the weird cases in your data is good. So here you see this once again. There I have the high greater conscientiousness, decide irrational, and I.mil once again. Now I simply type regression in front of it. And then I omitted the output, but looked at the diag2 command, and there you'll see, well, that same list of things that we had before. That part there. These are all measurements of, let's say, outlierness in different kinds of ways. These are the variables that I have in the data, because you can be an outlier in terms of the value that you score on a single variable as well. And you get an extra flag for every, let's say, sense of weirdness that you could have. So if you have a case that is an outlier in this sense, in that sense, in this sense, and that, and all these, then you get 1, 2, 3, 4, 5, 6, 7, 8, 9 flags. That would be somewhat suspicious. In this case, the maximum flags is actually 6. And this pattern looks pretty normal to me. 70 cases that have no flags whatsoever, so nothing suspicious. 5 that have 1 flag, 2 that have 3, and 4 that have 1, and 6 that have, 1 that has 4, and another one that has 6. So it's tapering off towards the end exactly as you would want it. So here I don't see anything bad in this output. Okay, yes?
Something that we already did, right?
Yeah. The only thing here is that in principle this is only supposed to work after regression. And we're now doing logistic regression. So that whole idea in principle is wrong, you could argue. But we can simply pretend that we do not know this and hope that, okay, even though the whole way of approaching this might not be right, if it leads me to an outlier, then it has worked. So it's, yeah, exactly. Okay, couple things left to do here. One would be the no multi-collinearity, and for that we have an extra command as well. Kind of nasty. This is one of the things that you typically get when different commands are made at different points in time. There is a command that we might remember from regression. First you run a regression command there, regress y on x, and then you type VIF for variance inflation factors. You get variance inflation factor scores, and you check if they are not too high. That's all old news. So again, it would be nice if you could type VIF right after logistic regression, but it doesn't work. And for that, you need another command that you need to install yourself as well. It's called collin for collinear. You can find it through either find it collinear or net search collinear. It's a bit more complicated to find it than the previous command, than the Idfbeta, because the output that you get from Stata is a bit longer. So you have to scroll and find in the set of 10 things that you get back which one is actually a collin command. But if you have installed this once, then it will work always. So that should be easy enough. Let's see. So yeah, there too, I have here an actual example. I'm typing here collin and then the 3 predictors that I have: conscientiousness, decider rational, and male. I get my collinearity diagnostics. One of the ways in which you can see that this is a homemade command is that the output doesn't look very nice. If Stata would have done this themselves, then in all likelihood this would all line out properly, but in this case it doesn't. You see here that these VIFs, that's the first column there, this one, so this one, that one, and that one. These numbers should be relatively low, as close to 1 as you can get them. And yeah, the rule of thumb was on average over 2.5, or you have a single one larger than 8, start to worry. There must be a variable in there that has another variable in the data that's closely correlated to it. Okay, but you know, the whole principle is actually the same as in multiple regression. So in that sense, there is nothing new. Okay, any questions up to here? It's awfully quiet. Right after lunch is all always about. Blood sugar is decreasing. All right. Then another one of these nice ones. Okay, we're trying to fit a model here, and we have to get a feel for if it's fitting. Not only if it's fitting well in the sense that I can predict 80% of my cases correctly, but also it is a good idea to model my target variable with the predictor variables in the way in which that I did it. And let's see how we can do this. Again, we type first our standard logistic regression. By the way, for all these commands that you type right after a logistic regression, make sure that you run this from a do file and not interactively, because it has to be obvious to you if you type, for instance, link test now, to which logistic regression it is referring back. If you type it in your do file right beneath it, this is obvious. If you are doing this interactively, it's not so obvious anymore, usually. So here the output is exactly the same. And now we type link test. And now we get something that is pretty similar actually to the OV test command that we've seen before. There the idea was exactly the same. We're trying to figure out, have we used all the transformations and the interaction effects that we could use here to make a decent model. You do that for a while, and then you check through that OV test command if there is any value in continuing to do this. And there we had something like, it was actually more complicated than here. The good news of that was that all that is happening behind the scenes, and here you actually see it. The OV test command was that you run your regression, you type OV test. What happens is you generate behind the scenes predicted values. These predicted values you square. You take them to the power 3 and to the power 4. None of that you've actually seen, but that set of raised to the power 2, 3, and 4, that you include as a predictor variable in your original model. And if that helps, that's bad news. That's suggestive of, well, trying to somehow transform your predictors in another way than you have done already is likely to help. And this is sort of similar in the sense that here you get your predicted values behind the scenes. That's the underscore hat variable. And that will usually be significant. Should be. We're predicting high greater. These are the predicted values, underscore hat. So these should be predictive of high greater, otherwise your model stinks. But this one, hat squared, shouldn't. So in the same way, so actually here we're missing hat raised to the power 3 and 4 compared to the OV test. Here we only have that squared value. And what we want here is that this thing does not end up to being significant. If this is significant, this is saying, well, the square of the prediction actually would have helped here. So fumbling around with your predictor variables in some other way than you have done might have been a good idea. If you have a value here above 0.05, great. This is suggestive of, well, quite a decent model, at least according to this test. Anything else I want to say about this? Let's see. I don't think so. All right. So that brings us to the last bit of logistic regression testing. That's the Hosmer and Lemeshow test. That's actually basically trying to do the same thing, but in a slightly different way. The idea there is, well, if my model fits well, it should fit equally well everywhere. Actually, more or less by definition. So if I look at, let's say, small probability values, there my model should be quite decent. Slightly higher probability values, there it should be quite decent, and so on. And what this command does is test exactly that. You divide your sample in different groups. Let's say, I think in the example in a minute, it will be 5 different groups. You check your observed zeros and ones with your predicted zeros and ones, and you get a measure for how well you are doing. And you compare, is that measure for how well you are doing equally good across the 5 samples that you have? And if that is the case, that's good news. If not, then your model is somehow misspecified and you have to keep plowing ahead. Here you see it. Again, you run this after a logistic regression, so if you just type this, then nothing will happen. GOF stands for goodness of fit. In this case, I specifically asked for 5, and I wanted a table to see, to show you in some more detail what exactly is going on here. So in this case, I divide my data in 5 different groups. From the lowest ones, the least number of ones to the highest number of ones. And now I see that if I look at my predicted probabilities, that the average predicted probability for this first group is 0.3. The average predicted probability for the second group is 0.4, and so on, all the way up to group number 5. Now what I can do is compare for each and every group. Okay, here I'm predicting 0.3 for this first group, and I see actually 2. There are 2 ones in that first group. And if I would go with the probability there, I would have expected 3.2. Okay, so that's not completely correct, but reasonably close. Here, I predicted 0.4. With that predicted probability on average, I would expect 5.8 ones in that second group. I find 7. And this comparison I make for all the groups that I have. And now I run an actual chi-square test on these 2 columns. I'm testing here, is this column here with obs1 in it the same as this column over there with x1 in it? And if it is, fine. Then my model apparently is equally good everywhere. So again, you want to have a value over there. You do not want to reject that these 2 are equal. One sort of issue here, as you have with many of these tests, now I took 5 groups. I could have used 6, 60, 600 if I have a large data set. And in principle, the test should work for each and every number that you use. That makes it a bit problematic because, it might be that it works for 5 and doesn't work for 10. So basically the only thing to do is, well, I'm taping myself, so perhaps I shouldn't say this, but normally what I do is you try it for a number of groups where the number of cases within a certain group remains, let's say, decent enough. So in this case, I have 80 observations. So with 5 groups, I have 16 in each group. So that is good enough to do something on. I wouldn't use 20 groups here. If I have 800 cases, perhaps I would use, let's say, 10 or 12 groups. And I try more or less at random 2 different numbers here. If it works out in the same way in both cases, fine. If it works out not in the same way for both cases, panic. Then you have to decide, okay, perhaps it's a good idea to keep plowing ahead and change my predictor variables. Perhaps not. It's not that obvious, at least not from this test. I would look at the link test in that case. Okay, what is that link test saying? Is that saying that it's more or less working? Okay, let's leave it at that. But it's not exactly obvious when to stop here. You can keep trying this, and at some point perhaps the test will actually fail. Okay, yeah, we have a couple of leftovers that I need, not 45 minutes, but I need some time for, and we'll do that after the break. Related to stuff that you can do as soon as the basic logistic regression stuff is done. Part of that we have seen before, but we can do a couple of extensions here that are useful to know. So all this is as soon as you have done and completed a logistic regression run and want to figure out how well your model is actually performing. And this is the left part at least we saw before already, that estat class command that will tell you something about how well the model is fitting. When, well, let's say somebody forces you to give an actual 0-1 prediction for the thing that you are actually predicting. You get a probability, but that probability can of course easily be transferred to 0 and 1, for instance by assuming, okay, anything below a probability of 0.5, that's a 0, and anything above, that's a 1. If you do that, you get the stuff on the left, that estat class command. All this, these 4 lines over there, that's, let's say, positive stuff. You want that to be high. All these are great. This is given that we have a 1, the probability that you actually predict a 1. Given that there is a 0, the probability that you actually predict a 0. Or here, given that you predict a 1, the probability that there actually is a 1. Or given that you predict a 0, the probability that there actually is a 0. All these you want to be high, 100% if possible. But here it's a slight bit lower. All the stuff below there, these 4 lines, are all bad things. So you want, all these are mistakes, and you want them to be equal to 0. Now, depending on what you're considering substantively, so the topic that you are studying, you might think, well, I'm very interested here in having that sensitivity value high. That is the probability that the true value is 1. The probability given that the true value is 1, that you predict that there indeed is a 1. So if there is a real 1, how likely is it that you will find it? If you find that very important, then one thing you could do is, okay, I change my predictions, and instead of only giving a 1 when the predicted probability is 0.5 or higher, I now also give a 1 when it is 0.25 or higher. So you give way more 1s. Obviously, if you're aiming to find a lot of real 1s in the data, then predicting more 1s is a good thing. And here you can see what it does, because if you add here the cutoff value, now 0.25 instead of 0.5, you see that this table changes, and among others, this sensitivity value also changes. The other values also change, so you have to somehow balance the gain that you now get for the sensitivity. Now it's 97%, great. But the specificity was 73, and it's not easy to see here, but is now way lower. The positive predictive value was 70, is now 55. Instead, the negative predictive value was 70 and is now 92. So depending on what it is you want to predict, how certain you want to be that you actually find the real 1s. For instance, if 1 is denoting a disease, you might be very willing to make sure that you actually find it. You may play around with that cutoff value, and you can put any value here that you want, including very low ones or very high ones. Okay, toying around with that is a bit of a nuisance, especially given that then 8 of these different numbers actually change. And most of the time, the two that we're most interested in is sensitivity and specificity. The 2 first ones on the positive list, so to speak. And if you type the lsens command right after you run the logistic regression, you get a graph like the one you see here. And this will give you, first on the horizontal axis, different values for the probability cutoff that you can choose. So the default, if you do nothing, is right there. And then you'll get, let's see, blue is sensitivity, a sensitivity of, well, is that 0.67? Looks like it, yeah. And the red one a bit higher, 73%, that should be indeed. Okay, so this is the 2 values over there and over there are the ones that you see over here. And here you see how the specificity and the sensitivity change as you are moving that cutoff value from left to right. The obvious focal point in the graph is where these two meet, as if something very peculiar is happening there, but there really is no need now to say, and for sure I know that people will do it at the exam, don't. Yeah, now we see that the optimal cutoff value is at 0.48 or so, because this is where these two lines meet. But you know, there's not a single reason to want that. Why would you ever like that they are necessarily of equal size? So typically what you would want to see is something like, well, in this case you don't see it so extreme, but here for instance, if there's a very flat piece, like here or there, in either the sensitivity or the specificity, then you know that if you are near that point with your cutoff value, you can move it from left to right without the sensitivity or specificity value changing a lot. So if it would be the case, we don't have that now, but here that the red line is increasing over there and the blue line is relatively flat over there, then increasing the cutoff value a little bit to the right makes it better in terms of specificity, and so in that sense it is useful to look at this graph in the hope that you can find where the sensitivity and specificity values get better for you, depending on the kind of topic that you're considering. It's a bit strange that, yeah, I must admit that I do not completely understand why that is, but from these four things, sensitivity and specificity are the ones that are always mentioned. Positive and negative predictive value, which in a way are just as useful, they're just slightly different. The first ones, sensitivity and specificity, are okay. Given that there is a real 1, can you find it? Or given that there is a real 0, can you find it? And the other thing is, if you say that something is a 1, how likely is it that that is true? I can imagine that that is equally important, at least equally important. But for this we do not have any separate commands that will show you how that value changes as the cutoff value changes. Okay, so let's see. Yeah, that the lsens command to give you an idea if it's smart to play around with that cutoff value a little bit. And the most complicated one, that ROC, that thing that you see over here, this curve is called an ROC curve. Receiver operating characteristic curve is called, and it takes a while to get used to this. The goal of the whole thing here is to come up with another measure for how well a model is doing. You could argue, yeah, we had already two. We had that pseudo R squared, and we also, what was the other thing? Let's see, the specificity you could take as one measure, the sensitivity or the total percentage of cases that you've predicted correctly. With all these, there are issues that R squared, yeah, it's really a pseudo R squared based on that likelihood, which is a bit strange. The total percentage of correctly estimated ones and zeros, yeah, this is highly sensitive to how many ones and zeros that you have. If you have a lot of zeros and you simply predict everything is 0, then yeah, it looks like you have quite a good model. And this is a little bit better. Now let's see what we have here. On the x-axis, we have 1 minus specificity. So let's see what that actually is. That's the probability that the true value is a 0 and that you then predict a 1. So you don't want that to be high. Okay, this is actually a mistake, so to speak. On the y-axis, we have sensitivity, and that is something that we do want. Okay, given that we have a true 1, how likely is it that you actually predict this? So this is something that we want to be high. Now let's see what happens with these two as we move the cutoff value, well, let's say from 1 down to 0. So first let's start here. There. This is the point in the graph where the cutoff value is equal to 1. Okay, the cutoff value is equal to 1. What does that mean? I am predicting a 1 as soon as my predicted probability is 1 or higher. Okay, so that's not happening. So I'm predicting a 0 here all the time. Okay, so here, this is where I predict a 0 all the time. So the probability that I predict a 1, given something, yeah, okay, that's 0. I'm never going to predict a 1. So we are here for the x-axis, and for the y-axis, well, the probability that I predict a 1, yeah, I don't predict a 1 ever. So I'm exactly there for the cutoff value equal to 1. This is where my graph is starting. Now the other side, cutoff value equal to 0. That means as soon as I have a predicted probability larger than 0, then I predict a 1. Okay, so that's basically saying I predict a 1 all the time. Well, that means the probability that I predict a 1 given something, yeah, I always predict a 1, so this is 1. And the probability that I predict a 1 given something else, doesn't matter. Here also, I'll predict a 1. And the dots here are the values for sensitivity and 1 minus specificity that correspond to different values of the cutoff value in between 0 and 1. And you get something typically that looks like this. And that thing is called an ROC curve. Now let's see. That yellow point over here, that's actually where you want to be. Okay, so the x-axis is a mistake. I predict a 1 and the true value was a 0. So I don't want to be to the right of the x-axis. And the y-axis, that's actually what I want, to predict 1 when the true value is a 1. Great, so I want to be here. So I want graphs that are, let's say, as close as possible to this point. Well, they cannot be near that point all the time because, as we've seen before, they have to start in the bottom left and they will end up in the top right. So, yeah, it would be nice if they get close to that yellow point, but they're certainly not going to reach that yellow point. What you could see here is that, well, if you look at this graph here, I have two of these ROC curves, let's say for two different models. Then you'll see for a given value on the x-axis over here, then apparently this one, the orange one, is better than the blue one because it has a higher value for sensitivity, which is good. So irrespective of where I look, this curve is better than that one. You can also look like that. Works the same way. You'll see that this curve, let's say shaping closer to that yellow dot over there, is better. And this has led to the idea, well, what we could use here as a measure for how well the model is performing, the area under the curve here. So we have half already. That's this part, this bottom triangle. And we have this one. And the more it is shaped like this, going upwards towards the yellow and then to the right, the better it is. And that value you get back from the LROC command. And this is typically, if you participate in any kind of optimization for a logistic regression, in data mining contests, for instance, if it's something that is binary that you need to predict, then almost always the thing that you need to optimize is the area under the ROC curve, and not something like the percentage of cases that you have correct, or the R squared, none of that. So this is the thing that normally is chosen to be the thing to optimize. It also allows you, a little bit loosely, but at least allows you to some extent to compare different kinds of models. You have the same data set and come up with a model and get an ROC curve value. I do something else, perhaps with totally different variables, and we can compare, let's say, who of us is actually doing best. Okay, again, LROC, you can only run it after you run a logistic regression. So Stata assumes that you've just run a logistic regression model before, otherwise it will complain and give you an error message. Any questions about this part? All right, then we're almost there, but there are quite a few things that you can still do afterwards that I did not talk about. You see here that the main things that are mentioned on top there, I went through those, so that eStat class, you can type classification if you want, but class is enough, so that we did. GOF for goodness of fit, that we did too, LROC and lsens as well, but there is quite a bit more beneath it. All these things you might need at some point. It's a good idea to browse through these kind of things. Some are also convenience commands. Given that you're running a logistic regression, it might be useful to know, and then one of these things that you can type over there, have a look yourself to try to figure out which of these are of use in which kinds of conditions. Some of these you won't need, for instance, that contrast I think we won't need at all that you see over there. But these and those are both useful commands, and I suggest you simply go through them yourself. Okay, then one thing that I forgot to mention, and it is nevertheless good to know, if you have run a logistic regression, you might remember from multiple regression what you could do to get the predicted values is type predict, and then the value, and then the name of a variable, and then you get predicted values in multiple regression. Here, it is not necessarily obvious what you mean. Stata needs to know, do you mean the predicted probabilities, or do you mean the predicted zeros and ones? Of course, if you ask for the probabilities, you could create the zeros and ones yourself if you wanted, but you have to ask in different ways to Stata. So if you just, after a logistic regression type predict y, then you get the probabilities. And if you type the y/xb behind it, then you get the number on the horizontal axis that corresponds to that predicted probability. Okay, so we had that flat S, minus infinity over there, predicted probability close to 0, plus infinity over there, predicted probability close to 1, 0 over here, predicted probability 0.5. If you type predict y, you get the probabilities. If you type predict y, xb, you get that number on the x-axis, if for one reason or another you need to have it. Okay, in principle, that's all there is to it. Y equal to a binary variable. Okay, the only thing to make sure up front is that that doesn't go wrong. That's the whole idea. If you don't do that, then you missed something way in the beginning. Multiple regression or ANCOVA or whatever you want to use is not the right thing to do here. You'll get all kinds of trouble. That odds ratio plays a role here, and that flat S in the end is the consequence of that. So it helps to be able to look at these things in terms of odds ratios, and it helps to get used to that 1 over 1 plus e raised to the power of, and then a weighted sum of x's. Maximum likelihood, for most of the examples that we have in wikis online, we are not running into any major trouble, I think. But it can certainly happen if you have larger data sets that Stata doesn't figure out soon enough that it is reaching a dead end, and that your analysis will keep running and running and running and running, and at some point you simply have to cut it down the hard way and say, okay, apparently it's not going to happen, and we're going to try again. But for the smaller data sets we have, it's not going to affect us that much.